Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Alright, homework for lecture 102. Problem number 1, show that the units for electric field can be written as volts per meter instead of newtons per coulomb. And then part B, show that K, which is equal to 9 times 10 to the 9 newton meters squared per coulomb squared, can be written as 9 times 10 to the 9 volt meters per coulomb. Number 1, 1 newton per coulomb is equal to, well, that's a kilogram meter per second squared times 1 over coulombs, because a newton is a kilogram meter per second squared, because the definition of force is mass times acceleration. And this is almost what I need. We need to remember that 1 joule, so 1 joule is equal to 1 kilogram meter squared per second squared, and that 1 volt is equal to 1 joule per coulomb. So that's where we're headed. So we see that the kilogram meters per second squared is almost what we need. We can multiply through by another unit of meters, making this meter squared per second squared times 1 over coulombs, but we of course have to divide out that meter that we put in. And so now I can replace this with joules, and that will give me, we're good. That gives me joules. That's 1 joule times 1 over C times 1 per coulomb, 1 over coulombs times 1 over meters. But this is just 1 joule over coulombs times 1 over meters, which is joules per coulomb. That is the definition of volt. So we can replace this as 1 volt per meter and done. And that's part A. Part B asks about K, which is 9 times 10 to the 9 newton meter squared per coulomb squared. But let's just look at 1 newton meter squared per coulomb squared. And we'll do the same thing. We'll replace newtons with kilogram meters per second squared. That's 1 kilogram meters per second squared times meter squared over second squared. I'm going to borrow one of the meters from here. So I'll write 1 kilogram meter squared per second squared times meters per coulomb squared. So this, kilograms meter squared per second squared, is joules. And so that gives me 1 joule meter per coulomb squared. And then I'm going to move one of the C's, one of the coulombs, underneath the joules, and I'll write 1 joule per coulomb, meters per coulomb. And that, of course, 1 joule per coulomb is a volt again, and so I get 1 volt meter per coulomb, which is what I wanted. Okay, problem number 2. 3 electrons are clamped on the corners of a 1 angstrom square. What is the electric potential at the unoccupied corner of the square? And B, how much work in electron volts is required to place another electron at the unoccupied corner? So let's start by drawing a picture. This is problem number 2. And my picture, I'm going to call this charge 4. I'll put it here. That's the unoccupied corner. 3, I'll put here. And then charge 2 I'll put here, and then charge 1 I'll put here. And the distance between all of these is just 1 angstrom. And the distance on the diagonals here, of course, is the square root of 2 angstroms, just by Pythagorean's theorem. And remember that 1 angstrom is equal to 1 times 10 to the minus 10 meters. So, part A. Let's just add up the potential. So we'll have a potential 4, 1. That's between the site, the unoccupied point, and charge 1, plus the potential between 4 and site 2, plus the potential between 4 and site 3. But that is just equal to, the potential will be K times E minus, that's the charge of an electron, divided by, well actually since it's going to be the same in all three terms, I'm just going to factor it out ahead of time. And so this will just be 1 over the inverses of the distances. So this will be 1 over 1 angstrom plus 1 over the square root of 2 angstroms, because between 4 and 2 is the square root of 2 angstroms distance, plus 1 over 1 angstrom. And so what does this give us? This gives us, and these are all in 1 over angstrom, so I can just, basically I can write it like this. I can write K as 9 times 10 to the 9. That's got the units of K. What the heck? We just did that, didn't we? Newton meter squared per coulomb squared, but I'm not going to write the units in here. Times the charge, E minus, is going to be 1.6, or really it's minus 1.6. I'll put a minus here. Put times 1.6 times 10 to the minus 19. And then times, I'm going to pull out the conversion for angstroms here. Since 1 over angstroms is 1 over 10 to the minus 10, I'll multiply all of this by 10 to the 10 times 10 to the 10 times, that'll be 1 plus 1, so that's 2 plus 1 over the square root of 2. And what do we get? Oh, I don't know. I put a negative charge in here. These are not electrons necessarily. These could be protons. I think I set it up to be positive charges. No, I said negative, so we'll keep the negative sign. My bad. So this is minus, well, we have 9 times 1.6, and that's really all the factors there. 9 times 1.6. And then for the powers of 10, we'll have 9 minus 19 plus 10. And that's kind of nice. Times 2 plus 1 over the square root of 2. And this just reduces down to, let's see, 9 times 1.6, so that'd be minus 39. And minus 19 plus 9 is 10. And somewhere, do I have a, this is supposed to be minus 10. My bad. Minus 10. Yeah. Sorry about that. When I pulled out the angstroms, I needed to pull out 1 times 10 to the minus 10. Yeah. So now this leaves this to be 10 to the 0, so it's just 39. And that's also accounting for the 2 plus the 1 over the square root of 2, which is a little more than 2, obviously. And this will be in volts. Part B asks us to find the work, right? So the work is just going to be minus E times the voltage. And the nice thing about that is that whenever you use units of electron volts, right, we get it pretty directly here. It's just going to be, where did I get the minus sign from? Sorry, I meant E minus. E minus times volts, that's the charge of the electron times the potential, and that will give us minus 39 electron volts. Now, of course, we could have introduced the charge directly and then converted to electron volts, so I'll just show you that so you can see it. The charge of the electron is minus 1.6 times 10 to the minus 19 joules times the minus 39 volts. But we are going to want to convert the joules to electron volts, so we'll multiply this as 1 eV divided by minus 1.6 times 10 to the minus 19 joules. You can see that these basically cancel out, and so I just end up with my minus 39 electron volts as before. All right, number 3. I'm going to do these 5 parts one at a time. So part A says, what is the kinetic energy of a 1 microcoulomb charge released from rest in a 1000 volt per meter electric field, uniform, at 1 meter from its starting point? Okay, let's see. So let's make a note of these. This is number 3. And we should note that the electric field is 1000 volts per meter. In the x direction, this is a one-dimensional problem. And the charge is plus 1 times 10 to the minus 6 coulombs. Okay, so part A. Well, the kinetic energy is just going to be equal to minus the change in potential energy, which will be equal to Q times V, potential, which is minus Q times the electric field times delta x. This will equal minus 1 times 10 to the minus 6 coulombs times 1 times 10 to the 3 volts per meter times 1 meter. And that will equal 1 times 10 to the minus 3 joules, or 1 millijoule. Okay, part B says, what is the change in potential energy in part A? Well, that one is easy, because as the kinetic energy has increased, delta U has decreased. So delta U we will write as minus 1 millijoule. Part C, what is the change in electric potential? Part C. Well, the change in electric potential is just equal to delta U divided by the charge. And so that's 1 millijoule, divided by 1 times 10 to the minus 6 coulombs. And that's equal to minus 1,000 volts, or minus 1 kilovolt. That's another way to write that. All right, part D. Find the function v of x if v of 0 is equal to 0. Okay, so that is if at 0 the potential is 0. If that's our default position, then we would write that v of x is equal to minus the integral from 0 to x e times dx. That's going to be minus 1,000 times x, evaluated between 0 and x. Sorry for the duplication of x's. Some people like to prime them or put another tilde on or something like that, but I just like to leave it the same. That's equal to minus 1,000 times x, and that, of course, is in volts. Okay. Find the function v of x if v of 0 is equal to 1 kilovolt. So now we're setting our, basically we're going to replace this 0 with 1 kilovolt. And so E will look like, so v of 0 is equal to 1,000 volts. That's a kilovolt. Then v of x will become 1,000 minus 1,000 times x, also in volts. All right, number 4. In the Bohr model of the hydrogen atom, an electron orbits the nucleus in a circular path with radius r. Part A. Using Coulomb's law for the electrostatic force between the electron and the nucleus, and Newton's second law with centripetal acceleration v squared over r, derive an expression for the kinetic energy of the electron. Well, let's take that part first. So this is number 4, part A. So that's basically telling us that we should use Coulomb's law. So we have K times E squared, where E is the charge of the electron, also the charge of the proton, divided by R squared, will be equal to the mass of the electron, m sub E, times V squared over R. That's just Newton's second law. So this is Newton's second law, and this is Coulomb. Set those equal to each other. However, the kinetic energy, Ke, is going to be equal to 1/2 m sub E V squared. So we can get that Ke squared over R squared will be equal to 2 times the kinetic energy divided by R. And then we'll just solve for the kinetic energy. And that says that the kinetic energy is equal to Ke squared over 2R. All right, part B. what is the potential energy of the electron at distance r from the nucleus? Okay, so now we want the potential energy. So B, well, the potential energy as a function of r is just going to be equal to the charge, minus E, times the potential V. But what's the potential? Well, the potential, this, is just Ke over R. So if I substitute that in, I'll get minus Ke squared over R. All right, part C. Calculate the total energy of the electron. That's the kinetic energy plus the potential energy at R equals 5.9 times 10 to the minus 11 meters in electron volts. Okay, so C. E is equal to the kinetic energy plus the potential energy, which I'll just write PE. And that is going to be equal to Ke squared over 2R, that's the kinetic energy, minus Ke squared over R, which is equal to Ke squared over R times 1/2 minus 1. And this, if we put some numbers into this, well, this will just give us minus Ke squared over 2R. And so plugging numbers in, let's see, we'll do it down here. We've got minus 9 times 10 to the 9 for K, times 1.6 times 10 to the minus 19 squared for the charge. Divide that by 5.21 times 10 to the minus 11 for the distance, and that will be minus 2.18 times 10 to the minus 18 joules. But we wanted it in electron volts, so we have to multiply this times 1 electron volt for every 1.6 times 10 to the minus 19 joules. Gives me minus 13.6 electron volts. Okay, and the last part. How much energy must be supplied to ionize hydrogen in electron volts? All right, well, that's an easy one. If we supply 13.6 electron volts, then we will free the electron, though at infinity its velocity will just be 0. If we want it to go any faster than that, then we'd have to provide just a wee bit more energy. But 13.6 electron volts is the ionization energy needed. All right, number 5. Consider a uniformly charged sphere of radius r. Now, don't make the mistake in thinking that this is a spherical shell. This is a solid sphere. Also, don't think of it as a conductor either. Okay, this is some kind of material that contains charge. Think of it as an insulator. And so each new layer that we add onto this sphere is going to have some amount of charge associated with it. So we're going to start with some small sphere of radius r that already has some amount of charge on it. Okay? And we're going to, in part A, calculate the small increase in the potential energy, du equals kq over r, dq, by computing the work done to add a thin layer of charge, dq, to the sphere. And we will use the relation that dq equals 4 pi rho r squared over dr. Of course, you see how we got that relationship. This is, just as a note, where did we get that? Well, q is equal to 4 pi r squared times rho, the charge density. And so if I differentiate that, I get dq over dr equals whoops, that's not right. That's not it's 4/3 r cubed. There we go. Yes, the area of the volume of a sphere is 4/3 pi r cubed. My bad. I used the surface area. Sorry. So if I differentiate this, right, I'll get 3 times 4/3, which just gives me a 4 pi, and then it'll become r squared rho, and I solve for dq, right, so I could move this dr over here, and that's how I get that relationship. So in part A, let's do the calculation. This is number 5, part A. All right, so du, the small change in the potential, will be equal to dq times the potential, V. And that's just dq times kq over r. But we're going to use Q. I'm sorry. I've already done this. We're going to use this relationship that dq is equal to 4 pi r squared rho dr. And so we can write this as kq over r times 4 pi rho r squared dr. So now we have everything in terms of dr. So this implies that du will be equal to k over r times rho 4/3 pi r cubed times, that's just the area of a sphere, times the 4 pi rho r squared dr, rho r squared dr, which is going to equal 16 pi squared over 3 times k rho squared r to the 4th dr. So I just replaced q with this equation here, 4/3 pi r cubed times rho, and simplified as much as I could. So that's part A. That's the increase in the potential energy given a small increase in the radius of the sphere. Part B. Integrate this du from r equals 0 to r equals big R to find the total potential energy of the uniformly charged sphere of radius r in terms of the charge density rho and the radius r. Note what, and that just tells you what the integral is going to be. The integral of r to the 4th is just 1/5 r to the 5th. For those that are calculus challenged, I guess we could say. So u will be equal to the integral from 0 to big R of du, and that's just going to be 16 pi squared over 3 times k rho squared, integral from 0 to big R of r to the 4th dr, which equals 16 over 3 pi squared times k times rho squared times 1/5 r to the 5th, and that will equal, just u equals 16/15 pi squared k rho squared r to the 5th. Okay, and then the last part. Express the potential energy from part B in terms of the total charge of the sphere using the relation Q total equals 4/3 pi rho r cubed, big R cubed. All right, so part C, we're going to use the relation, what was it, Q total equals 4 pi over 3 rho r cubed. We're going to use that relationship in here. So this, of course, implies that rho is equal to Q total times 3 over 4 pi r cubed. So we'll substitute that in here. So u is equal to 16/15 pi squared k r to the 5th times Q total times 3 over 4 pi r cubed. And that, we can do some simplification here. Let's see. Oh, we got to square this. Oh, that's nasty. Okay. So what does that give us? That's going to give us, we have the 16 over 15 pi squared k r to the 5th. And we'll get Q total squared times 3 times 3, I'll write that as over 16 pi squared r to the 5th. Let's see, so let's start canceling some stuff. 50, I'm going to write this as 5 times 3. So we can cancel 1 3 out of that. The 16 will cancel. The pi squareds will cancel. The r to the 5th will cancel, and we'll just be left with r to the 1. And so what are we going to get? U is equal to any other cancellations? No, I don't think so. So u is going to be 3 over 5 times k q total squared, all divided by big R. So this tells us that u is proportional to q total squared, and it's proportional to 1 over big R. Anyways, there it is.